As we mentioned in the previous video, motions in the sky refer to a lot of different things moving. So this lesson, what we're going to do is we're going to talk about the different types of revolutions, Earth's rotations, Earth's orbits, precession, what a barycenter is, eccentricity. We'll cover the equinoxes and the solstice, diurnal motion, things like the zenith, the meridian, and how all those affect what we see in the sky. This is synodic day. It's a 24-hour period. And when we say 24-hour period, we understand that that's based on the sun. The sun, and I have the orbit of Earth, okay? Now, when the Earth is going around the sun, it's also spinning like a top, okay? And it doesn't spin in place. It spins like a top and it moves. So at this point right here, if I was standing at noon on the Earth looking directly at the sun and I wanted to rotate around and look straight back at the sun, that would be 24-hour period. Now the problem is, as the Earth moves, what happens is that I started looking here and I ended looking here. Okay, so on day one I was at this part of the Earth, and then as I moved I should be looking here, but my perspectives shifted, and so it's actually more than 360-degree revolution or rotation, but it's a 24-hour period, and we can use an instrument like a sundial to mark that time. Now for a sidereal day, it's 23 hours and 56 minutes. So I'm in a different color. I'm going to draw on the same picture. Now if I started out looking at the sun on day one, 360 degrees later I would be going from here back to here, and I'm still looking at the same background stars. Now what had happened was I'm no longer facing the sun in the exact same position. There's a gap. There's actually a 4-minute gap between here and here. Now that's important because if I'm going to look at stars from night to night, the what's called diurnal motion, or the appearance that the stars are moving through the night sky, they're going to rise 4 minutes earlier every day. Sidereal day, based on distant stars. Synodic, or the solar day, is based on a 24-hour period. Earth's rotations, okay, the spin, right? It determines the day, and you know, we're obviously tilted, but we're spinning basically around the poles. And because of that spin, there's actually a bulge in the equator. This also causes your trade winds and your jet streams, which control a lot of the weather going through the country. Earth's orbit explains the seasons. So obviously this is not quite to scale, right? The Earth's orbit's not really this ovally, but it helps prove the point here. Over here is called apogee, and this is called perigee. Perigee is when the Earth is closer to the sun, and apogee is when the Earth is further away from the sun. Now, in the northern hemisphere, so we're looking at this portion right here, at apogee, when the Earth is further away from the sun, the northern hemisphere is pointing more towards the sun, and so this is where you get summer. And when it's closer to the sun, but the northern hemisphere is generally tilted away, this is when you get winter. Okay. Now this is a little bit hard to conceptualize, so we're going to draw another picture. So what we have here is I've got kind of a different version, and this is the Earth in the middle, and you notice I've drawn it without the tilt, okay? So the blue circle here is going to be the equatorial line, okay? That's the middle of the Earth. And then the green line, that's kind of this tilt here, at exactly 23.5 degrees is the ecliptic. Now again, the ecliptic is the line between the Earth and the Sun. Now, there's 4 points on this that help us understand our equinoxes and our solstice. So we'll talk about the equinoxes first. So this point right here and this point right here are not only times in the year, but they're also locations in the celestial sphere, exactly where the ecliptic and the equatorial lines match up. Okay, the vernal equinox is in the springtime, and it would be when you're coming out of perigee. And so if you're in perigee, you're wintertime, and you're leaving that, this one would be the vernal. Now this one down here is called the autumnal equinox, and that's where you're coming out of apogee and you're going into perigee. So you're leaving summertime and you're going into wintertime. This point where the sun is highest in the northern hemisphere, exactly 23.5 degrees high, is the summer solstice. Negative 23 degrees. This is the furthest south in the sky that the sun will be for us. This is the winter solstice. Earth's orbit controls our seasons in a couple different ways. It's not about being close to the sun or far away from the sun. In the wintertime, the northern hemisphere is pointing away from the sun. As it moves around and it comes to apogee, it's now pointing towards the sun. What that does is that puts the sun higher in the sky or lower in the sky, and that's what this diagram is trying to show. As the sun goes through this path, the apparent path around the Earth, it will cross the celestial equator in different spots. And so when it's really high in the sky, summer solstice; when it's really low in the sky, it's the winter solstice, and then the 2 equinoxes are the transitional points. So the interesting thing about this is that these are not only times throughout the year, but they're locations on the celestial sphere. This image right here I'll put up is probably a better diagram of what I was trying to draw, and I think you can see a little bit better what I was trying to explain. Precession. What precession is this tilt changing. It goes kind of back and forth every 26,000 years. Now this is important because directly above the North Pole right now is Polaris. The other star that we could be pointing at, if that precession maxes out, I want to say is Vega. Another motion that we have is called the barycenter. So the barycenter is this gravitational middle ground, exactly gravitationally between Earth and the Moon. The Moon is about 1/4 the size of the Earth, so it has some pull. We can feel that pull in the tides, right? It definitely has an effect on the Earth. All things with mass have gravity and pull. Because the Earth is more massive than the Moon, it has more inertia and doesn't move as much. So it's not as affected as the Moon is. And that's why the Moon is orbiting the Earth and not the other way around. But this barycenter is actually the gravitational center between the Earth and the Moon. And so obviously the Earth being bigger, its barycenter is not in the middle of the Earth like we would think. It's actually about 15 kilometers below the surface. And so technically the Moon and the Earth are both revolving around that barycenter. So what's that look like on a bigger scale? Well, if I had the sun and the Earth is kind of doing one of these little shifts, is being pulled by the Moon this way, and then the Earth is being pulled by the Moon this way. Eccentricity is how ovally an orbit is. For reference, a circle is a perfect zero. and a line is 1. And so we know that the orbit of the Earth is an ellipse, and so an ellipse will fall between 0 and 1. Pretty doggone close to a circle. And so our oval orbit, or our elliptical orbit, isn't very elliptical. An orbit, or the planetary orbits, you have two foci. You've got the major axes, minor axes. The sun is located at one of those foci. So the zenith and the meridian kind of work together. So in the celestial sphere, right, the zenith is the point directly overhead, or declination of 90 degrees, at any given time. So on the summer solstice at high noon, the sun should be directly overhead at 23.5 degrees north on the planet, right? The meridian would be the line going through that from north to south, directly through that zenith.